Global Positioning System GPS. The Global Positioning System is a bearing technology which provides equal accuracy and flexibility of positioning for navigation, surveying and GIS data capture. The GPS provides continuous three-dimensional positioning 24 hours a day throughout the world. The three-dimensional nature of GPS measurements also allows us to determine horizontal as well as vertical displacement at the same time and place. The technology seems to be beneficiary to the GPS user community in terms of obtaining accurate data up to about 100 meters for navigation, meter level for mapping, and down to millimeters level for geodetic positioning. The GPS technology has tremendous amount of application in GIS data collection, surveying, and mapping. What is GPS? GPS basic. The GPS uses constellation of 24 satellites continuously orbiting Earth and computers to compute position anywhere on Earth. The GPS is based on satellite ranging. That means the position on the Earth is determined by measuring the distance from a group of satellites in space. In order to understand GPS basic, the system can be categorized into 5 logical steps. Triangulation from the satellite is the basic of the system. To triangle the GPS, measure the distance using the travel time of the radio message. To measure travel time, the GPS needs a very accurate clock. Once the distance to satellite is known, then we need to know where the satellite is in space, and as the GPS signal travels throughout the ionosphere and the Earth atmosphere, the signal is delayed. To compute a position in three-dimensional, we need to have 4 satellite measurements. GPS satellites are so high up that their orbits are very predictable, and each of the satellites is equipped with a very accurate atomic clock. GPS components. The GPS is divided into 3 major components listed below: the control segment, the space segment, the user segment. The control segment. The control segment consists of 5 monitoring stations. There of the stations, Rio Garcia serve as uplink installation capable of transmitting data to the satellite, including new ephemerate, clock corrections, and other broadcast message data, while Colorado Springs serves as the master control stations. The monitoring station track all GPS signals for use in controlling the satellite and predicting their orbits. Meteorological data also are collected at the monitoring station, permitting the most accurate evaluation of tropospheric delays of GPS signals. Satellite tracking data from the monitoring stations are transmitted to the master control station for processing. This processing involves the computation of satellite ephemerate and satellite clock corrections. The master station are transmitted to the master control station for processing. This processing involves the computation of satellite ephemerate and satellite clock corrections. The master station controls orbital corrections when any satellite strays too far from its assigned position, and necessary repositioning to compensate for unhealthy satellites. The space segment. The space segment consists of the constellation of 24 Earth orbit Novstar satellites. The satellites are arrayed in 6 orbital planes within 4 satellites per plane, equally spaced 60 apart along the equator and inclined at 55 from the equatorial plane. The orbital altitude of about 12,000 miles each with orbital speeds of 12 several hours are approximately one half of the Earth period. Approximately 12 hours of 3D position fixes. The next block of satellite is called block IIR and they will provide improved reliability and have a capacity of ranging between satellites, which will increase the orbital accuracy. Each satellite contains four precise atomic clocks and has a microprocessor on board for limited self-monitoring and data processing. The satellites are equipped with thrusters which can be used to maintain or modify their orbits. The user segment. The user segment is a total user and supplier community, both civilian and military. The user segment consists of all Earth-based GPS receivers vary greatly in size and complexity. So the basic design is that simple. The typical receiver is composed of an antenna and amplifier, radio signal microprocessor, control and display devices, data recording unit and power supply. The GPS receiver decodes the timing signals from the visible satellite and having calculated the distance computes its own latitude, longitude, elevation and time. This is continuous process and generally the position is updated on a second by second basis. Output to the receiver display device, and if the receiver display device provides data capture capabilities stored by the receiver logging unit. GPS positioning types. There are basically two different types of global position as described below. Absolute positioning. The mode of positioning relies upon a signal receiver station. It is also referred to as standalone GPS because, like differential positioning, ranging is carried out strictly between the satellite and the receiver station, not on a ground-based reference station that assists with the computation of error corrections. As a result, the position derived in absolute mode are subject to the unmitigated errors inherent in satellite positioning. Differential positioning. Relative or differential GPS carry a triangulation principle one step further with a second receiver at a known reference point to further facilitate determination of point's position. Relative to the known Earth surface point, this configuration demands collection of an error correcting message from the receiver, reference receiver. Differential mode positioning relies upon an established control point. The reference station is placed on the control point, a triangulated position. The control point coordinate. This allows for a correction factor to be calculated and applied to other roving GPS units used in the same area and in the same time series. Inherent sources of errors. GPS errors source from random noise basis of large scale blunders. Noise error usually amount to location in occurrence of up to a few meters and are caused by receiver noise and pseudo random noise. Bias error result primarily from the addition of the selective availability signals, the intentional degradation of the signal by as a amount to approximately 2 standard deviation of the potential code resolution. AI navigator satellite generate different codes and this is changing and low frequency based. Other base errors include clock inaccuracy which if left uncorrected by ground control may result in minor errors. Atmospheric dynamics on account for errors of over 10 meters with tropospheric factors such as changes in air temperature, barometric pressure and humidity according for 1 meter or less. Oceanograph ionospheric delays up to 10 meters are possible due to upper atmospheric operations. Multipath based errors Generally, submitter in range are frequently unavailable caused by interference of signals by near receiver, inflections of waves, or other physical obstacles in the line of sight between the receiver and receiver. Blunders are systematic errors that may result from user mistakes, software problem, receiver failure, or control segment mistakes. Computer or human errors can cause position solution inaccuracies from 1 meter to over to order of magnitude greater. GPS applications. One of the most significant and unique feature of the global position system is the fact that the position signal is available to user in any position worldwide at any time. With a fully operational GPS system, it can be generated to a large community of likely to grow as through or multiple applications ranging from surveying, mapping, and navigation to GS data capture. The GPS will soon be a part of the overall utility of technology. Surveying and mapping. The high precision of GPS can process measurement together with appropriate adjustment algorithms provides an adequate tool for a variety of tasks for surveying and mapping. Using differential global position system method, accurate and timely can be carried out. Continuous kinematic techniques can be used for topographical survey and accurate linear mapping. Navigation. Navigation using GPS can save countless hours in the field. Any features, even if it is underwater, can be located up to 100 meters simply by scanning coordinates from a map, entering waypoint, and going directly to the site. Remote sensing and GIS. It's also possible to integrate GPS positioning into remote sensing using GPS is kinematic technologies depending upon the accuracy required. Real-time or post-processing will provide position for the sensor which can be projected to the ground instead of having ground control projected to an image. GPS are becoming very effective tools for GS data capture. The GS user community benefits from the use of GPS for accurate data capture in various GS applications. The GPS can easily be linked to a laptop computer in the field and with appropriate software. User can also have all their data on a common base with every little restriction. The GPS can help in several aspects of construction of accurate and WGS databases. Thank you.